He dropped small objects, and he showed that they all, according to legend, accelerated at the same rate, like so. All right, so this fact really impressed Einstein, and it led him to what he refers to as his happiest thought.
Probably sounds better in German.
Fair enough. So Einstein's happiest thought was basically that a person in free fall wouldn't be able to feel their own weight. So that if everything is really accelerating at the same rate, that a person wouldn't be able to tell the difference between being in free fall in a gravitational field and, say, floating in outer space. So said another way, you could imagine putting somebody in an elevator, say, with a bunch of objects, so they could even build a whole lab in here if they wanted to. And you let the entire elevator and all the objects in it free fall. Now this universality principle is going to say that everything in this elevator, including the elevator itself, is going to be falling at the exact same rate. And what this means is that there's no experiment that the person in the elevator can do in order to determine that they're actually in free fall, as opposed to just being, say, in outer space in the absence of a gravitational field. That these two situations are entirely equivalent to each other. Does that make sense? Okay. All right, but then if you take this principle to heart, if you take it seriously, there are very profound consequences for this. So what Einstein did is he extrapolated, or what you can do is you can extrapolate this principle, and you can say, okay, I believe in this principle, and in fact it's called the equivalence principle. I should say that. So I believe that if I do, say, a local experiment in a freely falling elevator, that the results shouldn't be any different than if I were doing this experiment in outer space in the absence of gravity. So what are the consequences for this? Well, you can ask what would happen if instead of giving someone in a freely falling elevator, say, balls or other objects to play with, you gave them, for example, a laser beam. So let's suppose that you have someone in an elevator, and they have a laser beam, and at a certain moment, they're standing at one side of the elevator, and they shine the laser beam horizontally towards the other side of the elevator, like so. So they're in an elevator, they have some laser pointer, and they point it out directly horizontally from them. All right, so what this equivalence principle is telling us is that this person in the freely falling elevator shouldn't be able to tell that they're freely falling. They should see the result of this experiment in the same way that someone in an elevator, say, floating in outer space would see. So in other words, what this person would expect to see when they shine the laser from one side of the elevator to the other is they should expect the laser beam to hit the opposite side of the elevator at the exact same height that they released the laser beam from. So this person here in the elevator would see that they had released the laser beam here at some height h, and that it would hit the wall on the other side at exactly the same height h as well. All right, but now imagine that there's somebody who's standing on the ground watching this happen. So this person is not freely falling in a gravitational field. So this person sees this guy in an elevator. They see the elevator falling. They see that at one moment in time, this guy fires a laser beam at height h. At a later moment in time, this elevator has fallen some distance now. And then at that moment in time, the laser beam is going to hit the other side of the elevator, but it's going to hit the other side of the elevator at exactly the same height h that it was released from. So to the person standing on the ground here, they see the laser beam fired at this position here, but then hitting the other wall of the elevator, which is now at a lower point in space. So for the person standing on Earth, this laser beam has no longer gone in a straight line. They've seen the light curve, and they've seen the light curve in the gravitational field of the Earth. So if you take this equivalence principle to heart, what it's telling you is that gravity bends light. Or said another way, it's not just matter that falls in a gravitational field, it's light that's going to fall as well. All right, so this is very profound because we're used to thinking of light as always traveling in a straight line. In fact, in construction, laser beams are often used to define the straightest possible line. So there are two different ways you can think about it. You can just, give up this notion.